Building a smart home energy management system isn't just about buying a few smart plugs and calling it a day. It's about creating a network of locally controlled devices that track consumption, shift loads automatically, and cut your power bill without feeding your usage patterns to cloud servers that sell behavioral data to insurance companies and utility aggregators. My name's Chelsea Miller, and I rebuilt my entire energy monitoring infrastructure last year after discovering my smart thermostat was uploading granular occupancy data every 6 minutes. You're listening to the Smart Home Setup Podcast. Quick note before we jump in. Everything you hear is researched, tested, and written by real people who actually use this stuff, but the voice you're hearing is AI generated to make production sustainable. I'm glad you're here, especially if you've been listening for a while now. And if this is your first episode, welcome. You picked a good one. New episodes come out every Monday, Wednesday, and Friday, so there's always something fresh to dig into. Let's get into it. This whole process reflects what I learned during that rebuild: which protocols actually work offline, which hubs phone home regardless of your settings, and which automations require zero external dependencies. You need a clear-eyed approach that prioritizes data sovereignty alongside efficiency. Now, let's talk about the essential hardware components you'll need. Before you write a single automation rule, you need hardware that can measure energy flow, control loads, and coordinate decisions locally. Every component here must function without cloud access. First, you need a local energy monitor using Zigbee or Matter 1.4. Deploy a whole home monitor like the Emporia View 2 energy monitor or the Shelly EM if you're comfortable flashing custom firmware. Check the link below to see the current price. The Emporia requires its hub for full offline operation. It measures 16 circuits simultaneously with plus or minus 2% accuracy, but it will attempt cloud sync unless you firewall its MAC address. Real-time sampling happens at 1-second intervals with a 3 to 5-second reporting lag to your hub. It continues measuring locally during internet outages, but won't update dashboards until reconnected. Next, smart plugs with power metering, and Zigbee is strongly preferred. You need individual load tracking for high-draw devices, space heaters, window ACs, dehumidifiers, gaming rigs. Zigbee plugs from Sonoff, Third Reality, or IKEA Thread-Free integrate directly with Home Assistant's energy dashboard without cloud dependencies. Z-Wave plugs work but introduce 50 to 150 milliseconds of additional latency. Wi-Fi plugs phone home constantly and usually require manufacturer accounts. You'll need a hub with a local automation engine. Home Assistant, preferably on a dedicated Raspberry Pi 4 or Home Assistant Yellow, or Habitat Elevation. Both execute automations entirely offline. Your hub must support Zigbee or Thread directly via USB dongle or built-in radio to coordinate energy devices without latency-inducing cloud hops. Avoid Samsung SmartThings V3, which requires cloud authentication even for local Zigbee automations. For temperature control, get a smart thermostat with local API access. The Venstar ColorTouch T7900 supports 100% local control via REST API, no cloud account required. Ecobee and Nest both require cloud authentication for automation integration, even when controlling via local network. They validate tokens through external servers. Venstar integrates with Home Assistant's climate component, so you can write automations using temperature thresholds and occupancy sensors without external dependencies. Use Zigbee or Thread motion sensors for occupancy detection. Energy automations need to know when rooms are actually occupied. Use sensors that report immediately. The Aqara FP2 with Wave Presence and Zigbee 3.0 has 50 to 100 millisecond response time, or Third Reality motion sensors with PIR and Zigbee have 200 to 300 millisecond response. Your automation logic depends on this data. If occupancy equals false for 15 minutes, then power off this device group. Avoid Bluetooth or Wi-Fi sensors. They introduce 1 to 3 second lag and require persistent internet for most automation platforms. Get a battery backup, a UPS, for your hub and modem. During power outages, your energy monitoring stops if the hub dies. A basic UPS like the APC Backup 600 VA runs around $70, keeps your hub, router, and Zigbee coordinator alive for 30 to 60 minutes, long enough to execute shutdown automations for sensitive devices and log the outage event. I use a Triplite 850 VA that powers the entire networking cabinet for 45 minutes under typical load. Without hub power, all automations cease and devices revert to last state for Zigbee or lose connection entirely for Wi-Fi. You'll also want power conditioning for sensitive loads. If you're running a home server or NAS as part of your energy system, line noise and voltage sags will corrupt data. A basic surge protector won't cut it. You need a UPS with automatic voltage regulation that stabilizes fluctuating input. That runs around $120 for 1000 VA with AVR. Energy-hungry devices like space heaters on startup or compressor motors create brownouts that knock Z-Wave devices offline. I've measured 8 to 12 volt sags during HVAC startup that knocked Z-Wave devices offline. Finally, set up network infrastructure that isolates IoT devices. Your energy monitoring devices should operate on a segregated VLAN with no internet access except for firmware updates which you manually whitelist. A basic managed switch like the TP-Link TLSG108E runs around $40, and a router with VLAN support, pfSense, OpenWRT, or Unify lets you block outbound connections while allowing local traffic to your hub. This is non-negotiable for privacy. I've caught supposedly offline smart plugs attempting DNS lookups to advertising trackers, even when their companion apps weren't installed. Moving on to protocol selection and hub configuration. Your energy management system must account for protocol limitations before you buy a single device. Not all protocols support the low latency, high reliability automations energy management demands. Prioritize Zigbee 3.0 for energy monitoring devices. Zigbee meshes self-heal, support 100+ devices per coordinator, and most energy monitoring plugs use this protocol. Latency runs 50 to 150 milliseconds for sensor-to-hub communication, 100 to 300 milliseconds for plug commands. Expect 99% plus uptime if you have 3 or more mains-powered Zigbee devices creating a strong mesh. Devices retry transmission up to 3 times before reporting unavailable, so build automations that check device state before executing critical actions. Thread is viable for new devices, faster routing, IPv6 native, but hardware selection is limited in 2026. Avoid Z-Wave for high-frequency energy monitoring. Z-Wave's 9.6 to 100 kilobits per second bandwidth chokes when polling 20+ devices every second for power draw data. On a 40-device Z-Wave network, adding 10 power monitoring plugs increased average command latency from 180 milliseconds to 650 milliseconds. Z-Wave works fine for thermostats and HVAC relays, which are low-frequency state changes, but not for real-time load monitoring. Use Wi-Fi devices only as a last resort and firewall them immediately. Wi-Fi plugs lack mesh capabilities. Each device hits your router directly, consume 10 to 20 times more power than Zigbee equivalents, and nearly all require cloud authentication. The exception is Shelly devices, which support local HTTP control and MQTT. You can block their internet access entirely after initial setup. I use 3 Shelly EM devices for circuit-level monitoring in locations where running Zigbee would require additional repeaters. They've operated offline for 14 months without issues. Configure hub-based automation engines, not cloud-based scenes. Home Assistant's automation engine executes locally. SmartThings smart apps require cloud round trips even for local devices. Test this by disconnecting your internet and triggering an automation. If it fails, your hub is cloud dependent. Here's a pseudocode example. If the time equals 1400, which is off-peak start, and the washing machine state is idle, and battery storage charge is greater than 80%, then notify the user that the laundry window is open with off-peak rates active. Local automations execute in 50 to 300 milliseconds. Cloud-dependent automations take 1 to 5 seconds and fail during outages. Matter 1.4 support is good for future-proofing, with caveats. Matter promises cross-platform compatibility, but in 2026, it's still maturing. Current limitations include that Matter doesn't yet support energy monitoring attributes in its data model. Power metering requires proprietary extensions. My recommendation is to buy Matter-compatible hubs. Home Assistant supports it natively as of 2025.1, but stick with Zigbee for energy devices until Matter 1.5 ratifies power monitoring specs. Back up your hub configuration weekly. Energy automations become complex quickly. 20 to 30 rules coordinating HVAC, water heaters, EV chargers, and battery storage. A corrupted SD card or failed update wipes months of work. My backup strategy uses automated nightly snapshots to a local NAS. Home Assistant's built-in Google Drive backup is a privacy nightmare. It uploads your entire configuration, including device names, network topology, and automation logic. Restoration time is 15 minutes from backup to fully operational, assuming your Zigbee network remains intact, because devices remember their coordinator. Now, let's get into load monitoring and baseline measurement. You can't optimize what you don't measure. This section establishes data collection, the foundation for every automation you'll build. Install whole home monitoring first. Before adding individual smart plugs, establish your baseline consumption. Connect current transformers or CTs to your main panel breaker, configure the monitor's calibration multiplier, usually 2000 to 1 for 200 amp panels, and let it collect data for 7 to 14 days. You're measuring always-on load, which is the flat baseline when everything's off, typically 200 to 600 watts for vampire draw. You're also measuring peak demand windows during morning and evening HVAC plus cooking, and phantom loads from devices that spike periodically, even when idle. I discovered a malfunctioning dehumidifier drawing 380 watts continuously during my first baseline audit. It should have cycled to 12 watts standby between runs. Tag high-draw circuits for individual monitoring. Your baseline data reveals the biggest energy hogs. Typical culprits include HVAC at 3,000 to 5,000 watts, electric water heater at 3,500 to 4,500 watts, EV charger at 7,200 to 9,600 watts, dryer at 5,000 watts, and range up to 12,000 watts. Deploy smart plugs or CT clamps to these circuits. Prioritize anything drawing more than 1,000 watts consistently. You can shift EV charging to off-peak hours, preheat water during solar production windows, or delay dryer runs until battery storage exceeds 70% charge. Measure standby power for all smart devices. Smart plugs, hubs, and displays consume 1 to 8 watts continuously. Use a kilowatt meter, around $25 and fully offline, to measure each device's idle draw. My network has 23 smart devices consuming 87 watts total standby. That's 3.8 watts average, which equals 2.1 kilowatt hours per day or $23 per month at 35 cents per kilowatt hour. Devices that don't need 24/7 operation, like decorative lighting controllers or secondary displays, go on master-controlled smart plugs that cut power completely during sleeping hours. Log power quality events. Not all consumption spikes indicate usage. They often signal electrical issues. Track voltage sags below 110 volts or surges above 125 volts for North American 120 volt standard, power factor below 0.85, which indicates inductive loads without correction, and brownouts, which are sustained low voltage. The Emporia View reports voltage in real time. Create automations to log anomalies. If voltage is less than 110 volts for 30 seconds, then log the event with timestamp and voltage and notify the user that a power quality issue was detected. I've used this data to identify failing breakers and schedule electrician visits before equipment damage occurs. Establish per-device consumption profiles. Over 14 days, your smart plugs reveal each device's typical usage pattern. You need average wattage, peak wattage, daily runtime hours, and cycle frequency. For example, a refrigerator averages 120 watts, peaks at 780 watts during compressor startup, and runs 8 to 12 hours per day in 20-minute cycles. The automation application here is, if refrigerator power equals 0 watts for 2 hours, then notify the user that the refrigerator is offline and to check the breaker or compressor failure. Anomaly detection catches failing appliances before food spoils or fire hazards develop. Let's talk about time of use rate automation. If your utility offers time of use pricing, and 68% of U.S. utilities do as of 2026, according to the U.S. Energy Information Administration, your energy management system must include automations that shift loads to off-peak windows. Map your utility's TOU schedule into your hub. Most utilities define 2 to 3 rate tiers: off-peak, which is cheapest and typically $2,100 to $1,400, mid-peak at moderate pricing, and on-peak, which is expensive and often $1,400 to $2,100 weekdays. In Home Assistant, create input select helpers with your utility schedule, then use template sensors to expose current rate tier. Account for weekends and utility-defined holidays, which have different rate schedules. Automate HVAC pre-cooling or preheating. Run your air conditioning harder during off-peak hours to pre-cool your home, then coast on thermal mass during expensive on-peak periods. Here's the automation logic. If time equals 1330, which is 30 minutes before on-peak, and current temp is greater than target temp, then set thermostat to target temp minus 3 degrees Fahrenheit for 30 minutes, then set thermostat to target temp plus 2 degrees at 1400. Expected savings run 15 to 30% on cooling costs, depending on home insulation. This requires accurate occupancy detection. Don't pre-cool if the house is empty. If the thermostat loses connection during pre-cooling, it reverts to last set point. So add a safety automation that resets to normal schedule after 60 minutes. Shift water heater operation entirely to off-peak. Electric water heaters consume 3,500 to 4,500 watts when heating and cycle 2 to 6 times daily. You need a 240-volt smart relay like the Shelly 2PM flashed with Tasmota in line with your water heater's breaker. The automation is, if time equals 21, off-peak start, then power on water heater for 3 hours, then power off water heater. If water heater power is less than 100 watts for 15 minutes, meaning heating completed early, then power off water heater. The safety override is, if water temp is less than 110 degrees Fahrenheit and time equals on-peak, then notify user that water heater override is needed because temp is critical and wait for manual approval. I've run this automation for 18 months. Water stays hot enough through evening and morning usage, and total water heating costs dropped 42%. Schedule EV charging based on rate tier and battery storage. Never charge during on-peak hours if you have off-peak alternatives. The automation hierarchy goes, if EV plugged in equals true, and time equals off-peak, and battery storage charge is greater than 90% or there's no battery, then start EV charging. Else, if battery storage charge is less than 90%, then delay EV charging until battery storage charge equals 95%. Most EVs have 1 to 2 second command delays via their APIs, like Tesla or Rivian. EV telematics transmit your charging schedule, location data, and state of charge to manufacturers, so I use a simple Zigbee smart plug on the EVSE instead of API control to avoid that data leakage. Defer pool pumps, dishwashers, and laundry to off-peak windows. Automation can't run the dishwasher for you, but it can notify you when rates drop. The user-friendly approach is if time equals 21 off-peak start and dishwasher power is less than 5 watts, meaning it's idle and loaded but not running, then notify user that off-peak rates are active and to start the dishwasher now to save 40 cents. Pool pump automation is fully automatic. If time equals 21, then power on pool pump for 6 hours. Measured savings are $45 per month on pool operation by shifting a 1200-watt pump runtime entirely to off-peak hours. Implement dynamic load balancing to avoid demand charges. Some utilities charge based on peak demand, which is the highest 15-minute average draw per billing cycle, in addition to energy consumption. Load balancing automation looks like this. If current demand is greater than 8,000 watts, which is a threshold below the utility penalty tier, and EV charging equals true, then pause EV charging for 15 minutes, wait until current demand is less than 6,000 watts, then resume EV charging. This prevents expensive demand charge tiers. My utility charges $12 per kilowatt for demand above 10 kilowatts. Avoiding one 12-kilowatt spike saves $24 per month. Now let's dive into automation logic and conditional rules. Energy management automations must be more sophisticated than just turning off lights when you leave. You're coordinating multiple devices, rate schedules, and environmental conditions, all while maintaining reliability. Use multi-condition triggers with timeout safety. Simple automations fail when sensors report incorrect states. The robust approach is if motion in living room equals false for 30 minutes, and TV power is less than 5 watts, confirming the room is actually unused, and door state equals closed, preventing cutting HVAC mid-entry, then set thermostat to eco mode. Otherwise, log a warning that the automation was blocked because conditions weren't met. Always include duration clauses. Instantaneous sensor readings produce false triggers. I reduced false positive automations by 90% by adding 15 to 30-minute confirmation windows. Implement graceful degradation for sensor failures. Your energy automations shouldn't crash when a sensor battery dies. Fallback logic looks like this. If occupancy sensor state equals unavailable, then use fallback schedule, which is preset times for HVAC and lighting, and notify user that occupancy sensor is offline and using scheduled fallback. Otherwise, use occupancy-based automation. This is critical for HVAC control. A failed sensor shouldn't leave you without heat. Test your fallback behaviors by disconnecting sensors and verifying automations execute correctly. Build hysteresis into threshold-based automations. Devices that toggle rapidly waste energy and shorten lifespan. The problem is when you say, if temp is greater than 72 degrees, then cooling on, else cooling off, it creates rapid cycling when temperature hovers at 72.1 degrees. The solution is to add a deadband. If temp is greater than 73 degrees, then cooling on. If temp is less than 71 degrees, then cooling off. Else, maintain current state. HVAC compressors require 5 to 10-minute minimum off time to avoid damage, so enforce delays. My HVAC automation includes 2-degree hysteresis and 8-minute minimum cycle time. Compressor runtime decreased 30% and efficiency improved measurably. Log all automation executions for debugging. When energy costs spike unexpectedly, you need visibility into what ran and when. On automation trigger, log the event with automation name, timestamp, device states, and trigger source. Execute actions, then log automation completed with timestamp and result. Home Assistant's built-in logbook tracks this automatically, but I export daily summaries to a CSV on my NAS for long-term analysis. This data revealed a failed thermostat schedule that ran heating 3 hours longer than intended for 6 weeks, costing $78 before I caught it. Create manual override mechanisms. Automations can't anticipate every scenario. Guests visiting, illness requiring different temperatures, unexpected schedule changes. The override pattern is if manual override switch equals on, then disable this automation group for 4 hours and notify user that automation overrides are active and will resume at this time. Otherwise, run normal automations. I use a Home Assistant dashboard button that disables all energy automations for 2, 4, or 8-hour windows. Guests can adjust thermostats freely without fighting my schedules. Override expires automatically, returning to optimized operation. Coordinate battery storage if you have it installed. Home battery systems like Tesla Powerwall, Enphase, or LG Chem enable aggressive load shifting. Advanced automation looks like this. If utility rate equals on peak and battery storage charge is greater than 40%, then draw from battery and disable high draw devices group. If utility rate equals off peak, then charge battery to 100% and enable delayed loads group. Most home batteries use proprietary APIs like Tesla Gateway API or Enphase Envoy, requiring local network polling. Latency runs 5 to 10 seconds for state changes. I don't have battery storage yet, but I've designed my automations to integrate it when economics improve. Lithium prices dropped 40% in 2025, making batteries viable for TOU arbitrage in high-rate areas. Before you declare your system complete, verify these critical points. For hardware confirmation, make sure your whole home energy monitor is installed and reporting accurate data to your hub. Smart plugs should be monitoring all high-draw devices over 1,000 watts. Your hub should be operating on Zigbee or Thread with no cloud dependencies. Network segregation needs to be active with an IoT VLAN and Internet firewall rules. UPS should be installed and tested for hub and network equipment. Smart thermostat should be integrated with a local API and no cloud authentication required. For protocol and connectivity, your Zigbee mesh should include 3 or more mains-powered repeaters for reliability. All devices need to be tested offline, disconnect internet, and verify automations execute. Document firmware versions for rollback if updates break local control. Hub backup should be configured to local storage, weekly minimum. For automation functionality, TOU rate schedule needs to be programmed and tested. Load shifting automations should be verified for HVAC, water heater, and EV charger. Timeout safeties need to be implemented on all conditional rules. Fallback behaviors should be tested for sensor failures, and manual override switches need to be functional and accessible. Logging should be active for all automation executions. For baseline data, you need 7 to 14 days of whole home consumption data. Per device consumption profiles should be established. Always-on load needs to be identified and documented. Power quality events should be logged, including voltage sags and surges. Peak demand windows need to be mapped to daily schedule. For privacy and security, monitor DNS queries for unauthorized cloud connections. Inventory device MAC addresses and apply firewall rules. Delete manufacturer accounts if devices support local-only operation. Disable remote access. Use VPN-only access if needed. Let's hit some frequently asked questions. Can I build an energy management system using only Wi-Fi devices? You can, but you shouldn't. Wi-Fi devices consume 10 to 20 times more power than the Zigbee equivalents, 2 to 6 watts per device versus zero point 0.1 to zero point 0.3 watts. They reduce your router's capacity because most consumer routers choke above 25 to 30 active clients and almost universally require cloud accounts for automation integration. More critically, Wi-Fi introduces 300 milliseconds to 2 seconds latency for coordinated automations. That's acceptable for turning on lights, but unacceptable for real-time load balancing that needs to respond to demand spikes in under 500 milliseconds. If you absolutely must use Wi-Fi devices, choose one supporting local MQTT or HTTP APIs like Shelly or Tasmota flash devices, and firewall their internet access immediately after initial configuration. How much can I realistically save with energy management automations? Savings depend entirely on your utility rates, baseline consumption, and automation aggressiveness. Typical results from my testing and reader implementations show 15 to 25% reduction in HVAC costs through pre-cooling and occupancy-based setbacks. 35 to 50% reduction in water heating costs by shifting to off-peak hours, and 10 to 15% reduction in overall consumption by eliminating vampire loads and scheduling high-draw devices strategically. In dollar terms, a household consuming 1,000 kilowatt hours per month at 35 cents per kilowatt hour, that's a $350 bill, might save $50 to $90 per month with comprehensive automation. That's $600 to $1,080 annually. The real savings come from avoiding demand charges if your utility imposes them. A single automation preventing peak demand spikes can save $20 to $50 per month alone. Return on investment for a complete setup, energy monitor, smart plugs, hub, typically runs 12 to 24 months depending on your consumption and rates. Do energy management automations work during internet outages? They work perfectly if you've built them correctly using local protocols and hub-based automation engines. My setup has survived 3 multi-day internet outages without affecting energy automations. Zigbee devices continue communicating with the hub, automations execute on schedule, and data logging continues locally. The only functionality you lose during outages is remote access if you use VPN or cloud dashboards, and any automations depending on external data sources like weather APIs for predictive HVAC adjustments. Cloud-dependent systems like SmartThings or most Google and Alexa-based automations fail completely during outages. Devices become unresponsive and schedules stop executing. This is precisely why I prioritize offline-capable hardware and local automation logic. Your energy management system should be resilient to external failures, not dependent on them. Here are my final thoughts on all this. Your energy management system succeeds or fails based on one principle: local control before optimization. Every device that phones home, every automation that requires cloud validation, every hub that stops functioning when AWS goes down, these are failure points that compromise both your privacy and your savings. I measure success differently than most smart home enthusiasts. It's not about voice control or app aesthetics. It's whether my energy costs dropped, whether my automations survived the last internet outage, and whether I can open Wireshark and see 0 unauthorized data packets leaving my network. Build your energy management infrastructure like you're preparing for your ISP to fail tomorrow, because eventually it will. The automations that keep running, the schedules that execute without external validation, the logs that accumulate locally without cloud uploads, those are the ones that actually deliver value. Cloud-free viability score, 9 out of 10. Energy management is one of the few smart home categories where offline operation is not just possible, but superior. Local automation engines respond faster, fail less often, and keep your consumption patterns private. The only reason this isn't a perfect 10 is that some utility-specific features like real-time grid pricing APIs or demand response programs require limited internet access, but core functionality operates flawlessly offline. That wraps up this episode of the Smart Home Setup Podcast. Thanks for sticking with me through all of that. New episodes drop every Monday, Wednesday, and Friday, so there's always more coming. If you found this helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It genuinely makes a difference. It's how other people who care about privacy and local control find the show. And make sure you're subscribed or following so you get notified the moment a new episode goes live. Talk soon.